right? The last couple sections we did was all about the binomial distribution for your discrete variables. So a follow-up question would be, what happens with continuous variables? And that's what that's a great question. Thank you for asking. That's what chapter 7 is all going to be about. It's going to be about what we do to find the distributions for continuous variables. So let's start at the very beginning, because the idea of what we have to do for continuous variables is a little complicated. So let's start with an easy example, one that's called the uniform probability distribution. What does uniform mean? In general, not math-wise. What does uniform mean? The same, all the same. Cool, great idea. Example 1 says, imagine that a friend of yours is always late. Let the random variable x represent the time from when you are supposed to meet your friend until he shows up. Suppose your friend could be on time 0, or up to 30 minutes late, with all equal intervals of time between 0 and 30 minutes being equally likely. For example, your friend is just as likely to be 3 to 4 minutes late as he is to be 5 to 26 minutes late. The random variable x can be any value in the interval between 0 and 30. That is 0 less than or equal to x less than 30. Notice that we could be like 0.5 minutes late. We could be 0.0375 minutes late. So this is now a continuous variable because we can't just have these distinct or discrete numbers. We're going to draw a graph to represent the probability of the likelihood that your friend will arrive at a certain time between 0 and 30 minutes. So here's 0 minutes, here's 30 minutes. Just to simplify this, we're going to pretend that this is happening in 5-minute intervals, because otherwise we'd have to do 1-minute intervals, and that's 30 dots, and that's a lot. So if I'm doing 5-minute intervals, that means I have from 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, and then 25 to 30. Let's pretend that those are better spaced out. Okay, it's all equally likely, correct? So that means if this is the probability of that happening, that arriving between 0 and 5 minutes would be this much. Between 5 and 10 would be this much. Between 10 and 15 would be this much. Do you see what's happening here? We have this uniform distribution. Again, pretend like these are all actually the same width because I did my best. But we have this uniform distribution of the probabilities. They're all equal probabilities, so they're all going to have the same height of the graph. Now on this one, notice that the difference between what we did last time, where we just like put a little stick that went up, is that since this is continuous, we don't just have a time at 0 and 5. We also have like 2.5 and 2.35. So I'm not going to just put like a dot and a stick. I'm going to actually draw like a shape, like a rectangle or something here. So we have these intervals. Again, we just took it in 5-minute intervals to make the actual like drawing portion of this easier, where all of them are uniformly the same. A uniform distribution. Because any two intervals of equal length between 0 and 30 inclusive are equally likely, the random variable x is said to follow what we call a uniform probability distribution, because they all have a uniform probability across a distribution. In chapter 6, we learned that when computing probabilities for discrete random variables, the value of the random variable is usually substituted into some sort of formula. But things are not as easy for continuous random variables. To resolve this problem, the probabilities of continuous random variables are computed over intervals of time. So between 10 and 15 minutes late, as opposed to 12.5 minutes late. We're going to give an interval. To find probabilities for continuous random variables, we use what is called a probability density function. So now it's not just a probability or a binomial distribution function, we are calling it a probability density function. My science friends, what in layman's terms is density? Layman, so like non-scientific terms, what is density? It's how like dense something is, right? Like how compact. That's a great way to think about it. How compact. So if you hear that word density, you're kind of thinking there needs to be like some area or some volume involved with the situation. And that's exactly what I want you to think. It's not perfect, but it gets us in the right area to think. A probability density function called a PDF, not like a PDF document, okay, PDF, probability density function, is an equation that is used to compute probabilities of continuous random variables. It must satisfy the following two properties, which are going to sound very similar. The total area underneath the graph of the equation over all possible values of the random variable must equal 1, because in every probability experiment, what do all probabilities have to add up to? 1. So the area of this shape that creates my density function has to add up to 1. The height of the graph, height, must be greater than or equal to 0 for all possible values of the random variable. Does that sound familiar? Because in any probability experiment, we said that each probability should be between 0 and 1. You can't have a negative probability. Same thing. That means the height can't be negative because that would be a negative probability. These are the same rules we've had since forever. But why are we doing this and why do density functions help us? Great question. How are density functions used to find probabilities of continuous random variables? We're highlighting this whole sentence. The area under the graph of a density function over an interval represents the probability of observing a value of the random variable in that interval. The area, we're going to put like extra emphasis on area right here. The area under the graph of the density function over an interval represents the probability of observing a value of the random variable in that interval. With our binomial discrete data, we are able to plug and chug some formulas. For continuous data, because it's continuous, we're going to have to work with areas underneath these curves. And if you know anything about math, we'll eventually get to the point, we will not in this class, shall I say, area underneath a curve is like the basics of why you do calculus. We are not doing the kind of stats that need calculus here. We're going to do a lot more estimating than computing because obviously this is a non-calculus based statistics class. But it is involved with calculus. So if you Google stuff online and they're doing calculus, you're in the right spot. Just try to find some easier examples that are estimating, which will be more like what we do. So let's see some examples first, just with this uniform probability before I scare you with some stuff. It says, refer to the situation in example 1, which is our friend being super late. What is the probability that your friend will be between 10 and 20 minutes late? Well, here is our probability density function. If it's all uniform probability and there's 30 minutes here, that means each minute has a 1 out of 30 chance of them arriving at that point because it's all uniform. So what is the probability our friend will arrive between 10 and 20 minutes? So if this is 10 and this is 20, we want to know what is the probability that our friend will show up in this time. We want to know the area of that rectangle because that would represent the probability between 10 and 20 minutes. So our formula for area, oh yeah, geometry moment. What's the formula for area of a rectangle? Length times width, but because we're going to be doing it like this and it's not like a real rectangle shape, we're going to do base times height. Is that okay with everybody? Same thing as length times width, but if we call it base times height, I think it would be a little easier. If we're looking at this formula, what is the length of the base for this rectangle? Don't overthink it. 10. Between 10 and 20 is 10. What is the height of this rectangle? 1 out of 30. So we have these two numbers. We have again, this is because this is uniform. So across this entire rectangle, the height is always going to be that probability of 1/30th. So our probability that our friend is going to arrive between 10 and 20 minutes, right? Probability that the random variable x is between 10 and 20 minutes. All we have to do is find the area there, base times height. 10 times 1/30th, the probability that x is between 10 and 20 is just 1/3. Which makes sense, because if he's always equally likely to get there and you get him a 10-minute window, that means 1/3 of the time he's going to arrive in that 10-minute window. This makes sense. We can also work these problems a little bit backwards, meaning if you were given the probability, you can figure out the base or the height, whichever one you're missing. So it is 10 a.m. So instead of calling this 0, I'm going to call this 10 a.m. Time 0. 10 a.m. There is a 20% probability that your friend will arrive within the next blank minutes. That means from 10 a.m. to some time, the area underneath that curve will be the probability P of x equal to 0.2, 20%. So our probability formula did not change. Area underneath this curve for a uniform distribution is still base times height. We know that the probability that it'll arrive in the next blank minutes is 0.2. What's this base measurement? If this is time 0 and this is time x, how long did it take me to get here? X. And then what's the height? 1/30th. So if I was solving this in maybe a way that looked cuter to solve, this is what I would be doing. 0.2, can you write that as a fraction? What is that as a fraction? 2 over 10. 0.2 is 2/10. And this is x over 30. 1/5. Yes, but sure. Hey, look, that's a cute little proportion. Cross, multiply, divide. Or if you're like, what if it doesn't turn into a cute little fraction? Great question. If this didn't look like a cute little fraction, how would you solve for x right there? Multiply the 30 on the other side. Either way, however you solve this, you end up with 6. So we have a 20% chance that our friend arrives in the next 6 minutes. So we have the idea of these areas being probabilities that allows us to solve questions. And that is for a uniform distribution. Rectangles. Nice, right? Unfortunately, not all continuous random variables follow a uniform distribution. For example, continuous random variables such as IQ scores and birth weights of babies have distributions that are symmetric and bell-shaped. Consider these histograms below, which represent, oops, I'm trying to turn you down, that represent the IQ scores of 10,000 randomly selected adults. So if we look at this first one, what's the class width here? How much does each of these bars represent?
50.
No, these bars right here. 25-ish, maybe, yeah, that seems big. And then like it got smaller, right?
Yeah.
And then it got smaller. What's happening to your rectangles that make up these curves each time I make my class width smaller? They're getting skinnier. What happens to what I'm going to call the error in trying to find the area? You see this curve? You might want to highlight it because it's kind of hard to see. You see this curve that's going up and down on all of these? Notice the amount of white space that's in the first one compared with the third one. How much white space, more white space is there here as opposed to this? What's happening to the amount of white space? It's getting smaller. So our rectangles, as they get smaller, become a better representation of the area underneath these curves. Finding the area of a rectangle is easy, yeah? Finding the area underneath the curve requires calculus. So we're going to use these approximations with these rectangles, taking the idea we have from that uniform distribution to approximate the normal curve. Okay. Again, if you wanted to color in these, they're technically pink or red or something, but if you wanted to color them in, just to show that we have these bell-shaped curves that are eventually going to work with. A continuous random variable is what's called normally distributed or has a normal probability distribution if its relative frequency histogram has the shape of a normal curve. So these are normally distributed because they look like a bell curve. They are normally distributed, as opposed to paranormally distributed. Check out my joke. You get it? It says normal distribution, paranormal distribution. That's funny. Okay. Move on. So let's talk. We're going to spend a lot of time talking about this normal curve. A lot of today is information, so just hang on with me as we color code and we highlight. There's very few examples. There's a lot of information. Recall from earlier chapters that the mode represents the high point of the graph of any distribution because mode is the most often. Median represents the point where 50% of the area under the distribution is to the left and 50% is to the right because it's the middle. And mean represents the balancing point of the graph of the distribution. I want you to highlight the word mean in red or pink because we're going to be doing that a lot today. For symmetric distributions with a single peak, such as the normal distribution, in fact, the mean is going to be equal to the median, which is going to be equal to the mode. That means we have perfect symmetry amongst our distribution. So for example, in this curve right here, this peak, it is labeled mu, so you know it's the mean. That is also the median. That is also the mode. Oh, hello.
I got you.
Because of this, the mean, again, we're highlighting pink for the mean, corresponds to the high point of the graph of the distribution. The points where x is equal to, I'm using orange for this, by the way, mu minus sigma and mu plus sigma, so one standard deviation above and below, are called the inflection points. So we have these inflection points where we take one step by the standard deviation away, both directions. Just FYI, because I teach AP Pre-Cal and thus a little bit into calculus, I'm going to call these points of inflection instead of inflection points. So you're going to see my acronym POI a lot. That is a me point of inflection. This is what I'm talking about. This point right here. Oh my gosh, I can't have class without so many things happening today. So here we are with our inflection points. One more word here. The points on the curve where the curvature or concavity, again, I teach AP Pre-Cal and that's a little bit of calculus tips. We're going to call that concavity because I can't help myself. The concavity of the graph changes. So if you notice, in between these 2 points, this part right here, would you say that's like a happy parabola or a sad parabola? Sad parabola. We're going to call that concave down. Because if you were doing your hands to make that shape, your hands would be pointing down, like your elbows would be pointing down, your wrist would be pointing down. So this section right here is called concave down, between your inflection points. Now if we look on the outsides here, do you see how it like flips over? And if we were making the shape with our hands, we'd do this. Look at my hands. I put my wrists together and my fingers up. That's called concave up. I know it's doing this, but it's concave up. Those are two concepts that tell us about the changes in that graph. So we have concave down sections and we have concave up sections. That's important. Let's talk about just for a second how the changes in mu, which again is your mean, and sigma, which create your inflection points, when they change, how the normal function will change, how this curve will change. So we have two examples here. For this first one, we're looking over here. We're going to compare the pink density curve that has a mu or a mean of 0 and a standard deviation of 1. All that I have done to make the blue one is I have changed the mean to 3. Notice the standard deviation didn't change. Here's some things we notice. We can see that increasing the mean from 0 to 3 caused the graph to shift 3 units to the right, but did not change its shape. So the mean basically tells you where to start this curve, where to have its most point, its highest peak. If, however, like the second example, we don't change the mean, meaning the middle point does not change, but we do change the standard deviation, we increase it by 1, we go from having the standard deviation that's high, 1 step away, to a standard deviation that's 2. What's happening with the graph? It got flatter, wider, I'll take both of those words. Changing it from 1 to 2 caused the graph to become flatter and more spread out, wider, but maintain the location of its center. So the mean and the standard deviation control a lot about what the shape of your normal curve will look like. If it's not very spread out, you're going to have a very high peaked and skinny graph. If you have a long or a wide standard deviation, it's going to be way flatter because your graph has to go a lot more to get that inflection point. So why do we study this? The properties of the normal curve eventually allow me to make a lot of conclusions about graphs. Y'all remember this from like chapter 3? No. She's back. In between one standard deviation of the mean, we know that 68% of data lives there. 2 standard deviations from the mean, 95% of data lives there. 3 standard deviations off the mean, 99.7% of data lives there. So this normal curve, which becomes a uniform empirical rule, will then allow me to make a lot of conclusions about my data if it's symmetric. Here's the things I need you to know. The normal curve is symmetric about the mean, mu. Because mean equals median equals mode, we also know that it has that highest point at mu. The normal curve has those inflection points. This is like a little summary page for you, by the way. Has those inflection points at plus mu and minus mu. Plus sigma and minus sigma. Because this is a normal distribution, the area under the curve is equal to 1 in total. Therefore, the area under the curve to the right of the center would be equal to 1/2, And the area under the curve to the left of the center would be equal to a half. It is a function that has end behavior of 0 because as x approaches positive and negative infinity, the graph approaches but never touches the horizontal axis. Ooh, this is why you took college algebra before you took this class. And thus the empirical rule is back. We learned about this in chapter 3. Approximately, I already said this, 6% of the data is between 1 standard deviation, 95% of the data is 2 standard deviations, and 99.7% of the data is between 3 standard deviations. So eventually, this allows us to make a lot of conclusions about your function. Let's see how this works. Example 3 says, the relative frequency distribution given in table 1, so this is a relative frequency. That means when we surveyed, however many people we surveyed here, 0.005 of them had height. What are these, babies? Yeah, 3-year-old females, there it is. Had this height. So we have a frequency distribution here. The raw data indicate that the mean height of the patients is 38.72 inches, and the standard deviation is 3.17 inches. It asks you to draw a relative frequency histogram of the data, but I actually already did that for you. And then draw a normal curve on the relative frequency histogram with mu 38.72 and sigma 3.17 inches. I also already did that for you. So if you notice, these frequencies are aligned perfectly to the height of these rectangles. In chapter 2, we learned how to do this, how to find your class width, your midpoint, and draw the histogram. That's what we did here. I figured you didn't want to do that again, so I did it for you. But if you notice, this normal curve, when I draw it on top of it, is a pretty good approximation of how this data will work. Obviously, there's some error here and here and like here, but it's pretty good, right? Okay. So we know now that we can fit this normal curve, a uniform bell curve, on top of our histogram, we know that all of the rules for the empirical rule take over. Part B just wants us to compare the area of the rectangle for heights between 40 and 40.9 inches, which, yes, is the section that is highlighted on green. It doesn't look green on your black and white copy, but it is that little part right there if you want to highlight it green. We're going to compare the area of that green rectangle compared to the area under the normal curve for that section. So as a sketch, we're going to come down here and we're going to draw some things. We're going to draw that green rectangle. Here's my green rectangle. I'm also going to draw an estimate of where that curve is at the same section. Meaning I'm basically zooming in on this part right here. So I have my green rectangle and my curve comes through it, yes? So there's like a little bit of extra hanging off over here and a little bit of extra unaccounted for right here. That's what I've tried to draw here. I've got a little bit extra hanging off and a little bit unaccounted for by my rectangle. Why we are able to use these rectangles to approximate the probability or the area underneath these curves is because if you look at this amount of area that's stuck outside and compare it to the amount of stuff that we did not cover on the inside, that's pretty close, right? So we're able to use just the rectangle without having to worry about the error here and the error here because they're approximately equal. So we would say, if we're comparing the area, we would say the rectangle is very close to the area under the curve, which allows us to make a lot of conclusions. We can do easy geometry of rectangles instead of having to worry about the calculus involved with doing area underneath this curve. It's a nice approximation. Those of you who take calculus, which I actually don't think anybody in here is doing both, this is where the Riemann sum idea came from calculus. So when we start actually computing stuff, what are we going to do? The equation or model used to determine the probability of a continuous random variable is called a PDF, probability density function. And just like our binomial density function or binomial distribution function, we have a formula here. But let me tell you this, we are not using it. Because big yikes, would y'all want to use that? No. Yeah, It really is only helpful when you understand the calculus involved. So instead, we're going to be working on finding the area underneath a normal curve in a different way, and we're going to wait till next time to actually do that. We're just getting the idea of what normal distributions tell us today. Once we do learn how to find the area underneath a curve, so yeah, if you wanted to not scare yourself, just put like no thank you. Right there, no thank you. If you take stats again in college or a calculus-based stats, yes, thank you. But for us, no thank you. It depends on what you study. Because some degrees need multiple stats classes. Just depends. Okay. The area underneath a curve. Cool. What does it even mean? Suppose that a random variable x is normally distributed with a mean of mu and a standard deviation of theta. Theta? What? Sigma. The area underneath the normal curve for any interval of values of the random variable x represents either A, the proportion of the population with the characteristic described by the interval of values, the proportion of the population, so applying it to the whole population, or the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. And that's what we're going to be worried about today, is just making our conclusions clear so that when we actually find the area, we already have the conclusion moment down. So example 4 is the big kahuna. It says, the serum total cholesterol for males that are 20 to 29 years old is approximately normally distributed with a mean of mu equal to 180 milligrams per deciliter? Med terms, friends? Deciliter? Yeah? Okay. And sigma, so this with a standard deviation of 36.2 milligrams per deciliter. Based on the data obtained from a National Health and Nutrition Examination Survey, draw a normal curve with the parameters labeled. We want the mu and the points of inflection for this graph. Meaning, I want to know the value here at the peak. But that should always be the mean. So what number should I label right there? 180. For good measure, we'll go ahead and put a little line. That represents 180. If it's normally distributed, that means most people should have a cholesterol of 180. Well, let me rephrase. Most males from 20 to 29 years old should have a cholesterol of 180. We also need the points of inflection for this graph, which are one standard deviation above and below this mu. So we are going to compute mu plus sigma, and we're going to compute mu minus sigma. You have mu and you have sigma right there, so we're going to do 180 minus 36.2 and 180 plus 36.2. What do you get? 143 point, what? 143, Miss Quigley, 0.8 milligrams per deciliter. 216.2 milligrams per deciliter. Do y'all see how he did that? Just adding and subtracting, which means that that creates these points of inflection for me on my graph. This is going to be the place where the graph changes concavity from concave up to concave down. 143.8 and 216.2. These are my points of inflection, just so we have it labeled. One more again. Part B is going to have us draw on this graph a little bit, and I recommend if you've highlighted some stuff, great, do this next one in pencil, and if you've done everything in pencil, do this next one in lighter pencil. It says an individual with total cholesterol greater than 200 milligrams per deciliter is considered to have high cholesterol. Shade the region under the normal curve to the right of x equal to 200. Well, obviously, where would x go on this graph? Like somewhere in between here, yeah? So we're gonna estimate that it's about here. And we're gonna draw a line and shade in the region that is to the right of that. Because that is all the places where cholesterol would be higher than 200. The question that you're going to be asked next class is, what is the probability that somebody has a cholesterol higher than 200? So you would be wanting to find the area underneath this curve all through right here. We're going to worry about actually finding that answer next class. But let's work on the conclusion. Suppose that you do what I'm going to teach you next class, and the area under the normal curve is found to, the probability, aka the area, is found to be 0.2903. Provide two interpretations of this result. If we move this back into the conclusions from that box, our first interpretation is that the proportion of 20 to 29-year-old males, that's the population, that has high cholesterol, because it's cholesterol over 200, which is considered to be high, is 0.2903. That's the proportion of our major population. Or, again, second bullet point in that box up there, not only does this represent the proportion of the population where this would happen, it also represents the probability that a randomly selected 20 to 29-year-old male has high cholesterol. So these areas underneath these curves give us two conclusions. They tell us the proportion of the overall population that has this characteristic and the probability that a randomly selected person from the population has this happen. So we're going to use this normal curve next class to find these areas and tell me probabilities or tell me proportions of populations. Our goal today is to get used to the idea of these normalized curves, with mu being the center and 1 sigma above and 1 sigma below being our points of inflection. Eventually we'll get to the empirical rule and finding these areas underneath the curve, but we haven't gotten there yet. That's next time. Questions, comments, concerns?